Hello and welcome to week 7. Probably one of the more important chapters. So I'm on my Macintosh today because my PC is just crunching a bunch of numbers. But hopefully the sound, video, all the quality is the same. Material doesn't really change. So like I said, you can have a Mac or PC for this class. Doesn't matter. Now, the concepts in this chapter are vital. Actually, go back so we see it. It's one thing to understand something. It's one thing to be able to know it. And it's another thing to be able to really use it and apply it. You know, I learned a lot of this stuff as an undergrad. I'm sure you've heard of most of this stuff before. But I think it's really vital that you can take this information, change it, and use it in your experiments and in your life. Because a lot of times in business, they'll make basic assumption errors on hypothesis testing on a lot of these tools, and it can cost businesses thousands, millions of dollars. It can be really bad. I have some examples of it, but it's just all over the place. And it's not anything that they're doing or not doing. It's just they don't have a firm background in statistics. And, you know, I didn't. I mean, I had to do this 10, 15, 20 times, and I still sometimes get with these really rare cases where I'm like, let me think about this for a couple minutes. So, again, nothing in here is technically mathematically hard or logically complex, but it's just something that you really have to know in and out and know well. So I do have the book next to me. I might reference the book once in a while. There's some things that aren't as detailed as a book, and there's some things that are much more detailed in the book. But I follow basically the same outline as a book. I just go into a few more details. And like I said, I think this should have been probably one of the first chapters that we went into. So, again, you know, we've talked about this. What is a population? A population includes all members of a defined group you're studying or collecting. Just all members, okay? Now, why is this important? Because sometimes we can't always get all the members. We can't always contact all the members. Sometimes it's just too expensive to do, even if we can. Let's think about this. This is a census. So the census cost, the 2023 census, $13 billion. It's a lot of money. It's a lot of money. That's like $50 every person in this country to run a census. And they do it every 10 years. They get $1,000 over a lifetime. And the census, the idea of the census is to get the population. Now, they know they can't do that, but at least it's, you know, that's what their goal is. So we could take a sample and in doing so, or by taking a sample, hopefully it's representative of the population. Otherwise, it wouldn't be a very good sample. Now, there's a whole science into sampling. And like I said, that's one of the areas that businesses maybe fail or maybe not do as well because they do a quick sample and they forgot a lot of the basics of sampling, things like that. A lot of the issues I see with a lot of work is the samples aren't valid. They're not good samples. But, you know, like I said, just remember at the end of the day, you have a population, which in theory is everyone, right here. And we can try to measure everyone, but it's very, very, very expensive. I mean, like with all the fish, I mean, try to measure how many salmon are in a river, in the ocean, whatever. Or we can measure a sample. And a sample can be much cheaper, but how accurate is it? How well does it represent the population? There's different approaches based on the need of the population, and there's basically two types of populations: finite population, which everything's fixed, and infinite population. So the number of cells, maybe in a body, the number of stars in the universe. I know that's one question people sometimes ask is, what's an infinite population? It may not be infinite, but it's so large you can't count it very well. Um, so statistical inference is the idea we take that sample and we kind of predict the population. Super easy idea. We sample X amount of people from the population, and then we try to predict the population. There's a couple different ways of doing it, but some just key terms, big picture idea is, a point estimate is basically just a mean of, a point estimate is basically just a mean or some type of, I guess, average of the sample. Okay, it doesn't always have to be a mean, but it's generally a lot of times a mean. And we're trying to say, hey, this is the mean that is a proportion of the population. The interval estimate is basically, so I'm just trying to think of these in as easy as to explain terms. So basically what we say is, hey, if we know that we think, we took a measurement of 50 people, and that the average male will be 6 foot, okay, that's the point estimate. We can say, hey, with a 95% confidence rate, the average person is between 5'9", at UNLV, the average male between 5'9" and 6'2". That would be the interval estimation, 5'9" to 6'2", for a confidence interval. Now, the one thing that's kind of weird when you get to confidence intervals, as your confidence interval gets tighter, 99%, 90%, a little bit more relaxed, your interval estimate basically goes the opposite direction you think it will. So if you have a 99% confidence, what's going to happen? If you have to make a bet, if you had to make a bet with me that the average person, the average male at UNLV is between what two height ranges, you had to be 99% sure. You'd be like, I don't know, 5 foot and 7 foot. Just make it really big. If you had to be 90% accurate, be like, I don't know, 5'5" and 6'5". And so just kind of keep that in mind, that as the confidence interval increases, the interval estimate generally expands. We'll go into detail about this here in a second, but so a point estimate, the official definition is providing a single best guess, a point estimate, a single number of the population's parameter based on your sample. To estimate the average height of all university students, you take a random sample of students, calculate the sample mean, and use it to estimate the population mean. Your book has a good little graph for, I think, salary on 7.2. I have it in this note, so don't worry, I'll show it. So common point estimators: sample mean, the average income, sample proportion, sample variance, sample median. And we've gone over all these, you know what they all are. It's just, we're taking a number from our sample and trying to apply it to the population. Now, here, this is what I was talking about earlier, or at least part of it. What makes a good point estimator? Well, it's unbiased. So what do you mean, Richard, it's unbiased? Well, did you take only students that showed up on campus and measured their height? Maybe. I don't have any classes in person. What about all the students that take classes remotely? Maybe they're really short, maybe they're really tall. I don't know. So unbiasedness is a huge issue. So when we look at the polling predictions for the presidential race and things like this, well, there's a couple things you need to take in mind. That whenever they call me, I don't answer because I don't have time. So right there's a bias there. Are you using a phone list? So if I look for people's who they think is going to win the presidential election, and I get a list from, I don't know, the police department versus a randomly generated number, there's going to be huge differences in bias. Okay. Consistency, efficacy, sufficiency. So when we think about, like I said, point estimators or survey data or getting data, you really have to think about this. I think your book actually goes into one more, but there's whole articles you can go into. But when you start collecting a sample, when you start doing research, you really have to start thinking, how am I going to prevent bias? It's a huge problem. A lot of research right now is done on college students, and then we apply it to the whole population of America. Well, what's the problem? Most colleges have students between 20 and 30 years old. And it's hard because that's not the average age of most Americans. But yet a lot of research on campus happens between those ages. Okay. This is what I was talking about. So in your book, they talk about, I think, EA Arts, maybe some other company. Yeah, it's Electronic Associates, which I think is another company. So they got all 2,500 employees and said, hey, what's that the population's average salary, basically, mean salary, $71,000, let's just say. The standard deviation is 4,000. They had some stupid management training, 60% completed it, okay? So that we know that is what they call the ground truth. They got everyone, they figured it all out. They interviewed all 2,500 employees and said, hey, if you don't answer this question, you're going to be fired. You've got to answer this question. Have you taken the management training program? Well, again, that's not very practical. I mean, Optum has 300,000 employees. Walmart has, I think it was like 1 million employees. You just can't do that, okay? So what if we just take, a random, I don't know, 5,000 employees and grab that sample, grab their salary, 71,000. Well, it's pretty good. The deviation, it looks pretty good and things. So it's a lot easier to take a smaller, accurate sample than the whole population if possible. Now, I know we went a little bit into distributions and central limit theorem, I think 2 or 3 chapters back. Might have even showed some of these same graphs. But basically, if we have a good sample distribution, it allows us to make predictions, inferences about the population. Okay, they form the basis of many of our statistical tests. So if we know if we have kurtosis or skewedness in our data, and our data has a certain distribution, it's not bell-shaped, we have to use different math formulas, different tools in order to get predictions about a population. Okay. And you can kind of see here, so here's the population distribution. And if we just sample 2, it doesn't work really well, So it's always important to really keep, hey, is our distribution, is it bell-shaped? Is it gamma? What does it look like? Okay. It's a little bit beyond the scope of this course to actually dig into the reasons why and to really understand it, but as long as you know, hey, am I dealing with something that has a normal distribution, or am I dealing with something that doesn't? And there's when you use Excel or when you use SPSS or SAS or Python, it can tell you, hey, this is a normally distributed, or it's not normally distributed. If it's not, then we do something else. Yeah. So now confidence intervals. So because this is a vital thing that we really need to understand. And I wish I could give you a better way to understand it than like, hey, I'm going to make a bet with you. But that's the easiest way to do it. That's a way, I just kind of memorize it that way. Maybe you can come up with a better analogy in your mind. But if I have, the mean of 68 inches and the deviation of 10 inches, so 10, and I have 25 people. Well, if I want to have a 90% confidence, well, 65-ish to 72. Well, yeah, that kind of works because again, I'm 90% sure. It's a narrower range, and it's hard to think, but you're going from 65 to 72 because again, you have less certainty. You're 90% sure, 90% chance that you can win a bet. If you're on I don't know, maybe doing some type of sports betting, and you had a 90% chance to score between here and here, well, that works. But notice when you kick up to 99% confidence, I want to be 99% sure that I'm getting the range of these people. These 25 people, their average height is 68 inches, standard deviation is 10. Well, now I'm going to go from, I don't know, 65 down to 63. I'm going to add an inch to make them shorter. And also, I'm going to add, 2 inches to make them taller. Why? Because I know that I'm covering more of my bases. I wish I could give you a better analogy than that, but that's always the way I think about it. So when people present statistics, normally they give you 95% CI, but that's not always the case. And sometimes if they don't, you got to wonder why not. Are they trying to make the numbers look bigger? Are they trying to make the numbers look smaller? What are they trying, why do they not report a 95% confidence interval? So the interval estimate is a range, is this right here. Your confidence interval, your CI, is right here. The interval is based on the sampling distribution of the estimate, and the width of the interval depends on the confidence and the sample size. That's a key issue. So if we would have had 50 people, 100 people, 200 people, these numbers would have gotten smaller. Why? Well, because I have 200 people. I mean, it just, I don't want to say it just makes sense, but it just makes sense. I mean, if you have to make a bet with me for, let's say, $50, that I don't know, the average height is, between, I don't know, 62 and 70, but you only have 25 people, you're like, I'm not 100% sure. But if you have 1 million people, I mean, if you really have 1 million people and their sample mean, okay, is 68, 70, it doesn't matter, but you have 1 million people, you're pretty sure the next 2 or 3 people will fall within that range. When you have 25, you're not so sure. So sample size plays a huge part of this. There's a saying in a lot of computers, if you have, I don't know, 25, 50, or 100 kind of samples in your data, it's hard to reach statistical significance sometimes because you're not sure that it's there. If you have 1 million or 2 million samples, dude, you can reach statistical significance on very small changes. So what affects my CI? Sample size. That's generally the number one thing that can affect it. Larger samples lead to more narrow intervals. Standard deviation. I mean, if everyone came in and the standard deviation was 2 inches, well, then hey, I have 100 people. Standard deviation is 2 inches. I can kind of tighten up my intervals. If the standard deviation, everyone comes in, the mean is 72, but my standard deviation is 3 feet. I have no idea what the next person could be. Okay, so sample distribution, the variability of the sample size. Is it normally distributed? Are we looking at normal distribution? And our CI interval estimation. Okay. Let's keep going. So now, hypothesis testing sounds so simple, yet it's not. And a lot of people fail in this area. A lot of businesses, and it takes a while to get to it. Because we think of hypothesis testing as, this scientific thing done in the laboratory, but it's not. Do I like this type of food? Do I like this type of restaurant? Do I like this better than that? And how much, I don't want to say how much better, but I guess how much better. But basically one of the key goals is you have to state your null hypotheses, and we'll go into this. But your null hypotheses is, what if nothing changes? Then we have to collect data. You have to perform some type of statistical test. Then, based on the statistical test we perform, we either reject or fail to reject, or we reject a null, or we keep our null. Then we present our findings. let's dig into this a little bit more. There is something called a p-value. I'm sure most of you, if not every one of you, have heard of p-value. Okay. The problem is that p-value is really not the best measurement of if something is significant, if it's true, if it's important. Okay. I will put this link in the webcam. It's a good read, but a p-value, just because something is significant, doesn't necessarily mean it's true. There's a lot of other factors, effect size. I mean, there's a million other things. You know, that's why I just thought about p-value in terms of importance. So just don't, you know, just because something is statistically significant, that doesn't really mean that it is true. Okay. So now, hypothesis testing. Hypothesis testing, the basic idea is that you have a null hypothesis and you have an alternative hypothesis. Your null hypothesis is basically where nothing changes, you know, and that is very hard to comprehend sometimes. But if nothing happens, we keep the null. If something happens, we reject the null and we accept the alternative hypotheses, which I know sounds crazy, but you know, that is why it's hard to test metaphysics. That's why it's hard to test for aliens. Okay. So, you know, if we think about aliens, and it's just hard because, you know, these aren't necessarily real scenarios, but the null hypotheses would be something like there's no evidence of extraterrestrial life in the universe. So there's no evidence of extraterrestrial life. So that's all null hypotheses. We don't do research saying, hey, there is evidence of extraterrestrial life. That's not how you do it. You look and say, hey, my null hypothesis is that there's no evidence. And then I have to kind of prove that wrong, and then I have to accept that there is evidence of extraterrestrial life. Let me think if I can think of another example. And you know, I just thought about this. I have on my other desktop an example I'm going to show you. But so, you know, if we take a null hypothesis that ESP, you know, like how you can like read people's minds, ESP does not exist, and it has no effect on natural events. Okay, now this is basically untestable. Okay, now, so now that you have a good idea of what a bad null hypothesis is, do I have a good null hypothesis? Like, let's see, maybe this one. So, yeah, the null hypothesis is assumed true until evidence suggests otherwise. So, okay, so I have a lucky iPhone watch. I have a lucky quarter. Let's say that I have a lucky quarter. So my null hypothesis is that my lucky quarter does not increase a person's chance of winning at a slot machine. Using my quarter does not increase my chances of winning at a slot machine. So the alternative hypothesis would be using my quarter does increase my chances of winning a slot machine. Okay. And like I said, I know it's kind of hard to wrap your mind around it if you're not really used to doing it, thinking in nulls. So if I have, you know, my lucky quarter and I go and play a slot machine and I put 20 bucks in and whatever I get out. And then somebody else goes and, you know, doesn't use it. And then I give my lucky quarter to my wife and she goes and plays a slot machine and I get all this data. Then I can make I can do a statistical test on that data. But remember, my null hypothesis is that my lucky quarter, does not increase my chance of winning a slot machine. Because what I need to do is I need to see that my quarter does increase it. I need to accept my hypothesis. I need to reject the null. Okay. I know it's a bit confusing and it almost is counterproductive and counterintelligent. But once you really start getting into it, you'll say, oh my God, I know why I'm doing this. Okay. Why is it not going to the next slide? Oh, did I not? I guess I jumped the gun on that one too much. There is a type 1 error when you accept or reject a null hypotheses. There's type 2 error. There's a couple others, but let's just stick with this. And I remember this from a long time ago. That's why it's so blurry. So a type 1 error type 1 is basically when I'm trying to think the easiest way, you reject the null hypotheses, you get a false positive. So he took a pregnancy test, or he got a disease and saying he's pregnant. Obviously he can't be. So our null hypothesis was that my lucky quarter does not increase my winning on my slot machine. Okay. Well, a type 1 error, it would be saying it does. When I know it doesn't. After I run my experiment, blah, 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 I conclude that my lucky quarter increases the chance of winning at the slot machine. And we know that's not true. We know that a lucky quarter in my pocket's not going to change the slot machine. Now, a type 2 error, you can't really use that to lucky quarter thing there. But let's say that you have some type of magic magnet that cheats the machine. Okay, and then you say, hey, my magic machine doesn't work when it actually does work. So basically, 1 is a false negative, type 2, and 1's a false positive. And so, again, it's hard to convey this and not be in front of you, looking at your faces, making sure you understand this. False positive, and again, some things are worse than others. Sometimes a type 1 is bad, sometimes a type 2 is bad. It depends on the data, or depends on the case. But at the end of the day, you don't want to be making either one of these if you can help it. We make tables in programming or in data science, and it shows how many times we get a false positive in our model. Okay. Let me keep going because I think I have more on this. It's so important. So yeah, rejecting the null hypothesis is actually true, also known as a false positive. Example, concluding a drug works when it doesn't. And we've seen that with the FDA. Or concluding a drug doesn't work when it really does. So I don't really want to call it a type 1 error, but some doctors say you should take a baby aspirin every day to reduce heart disease. Well, looking at the data over more long term, it doesn't work. It has too many side effects. It's more dangerous than it's helpful. There are certain drugs that have been rejected by the FDA, but they work. Maybe they just don't work strong enough, but that's a different issue. So really kind of keep this in mind, maybe screenshot it. I just really want you to know this. False positive. Hey, you're pregnant. Hey, you're pregnant, and no, you're not. I'm looking at you and you got a little baby, No, it's not. So again, just try to remember that. So here are some real life impacts of type 1 errors. Early in the pandemic, tests in the UK produced false positives. This led to unnecessary quarantines and public health concerns, and it's just horrible for the public image. The null hypothesis is a person is not infected. The alternative hypothesis is the person's infected. Well, the person was not infected, but it's a type 1 error, so we label them as infected. Duke Cancer Research. Researchers have claimed to found a way to predict a person's cancer outcome. Later, it was discovered to be based on flawed data. So our null hypothesis is that there was no relationship. We couldn't predict it. We did a type 1 error, or somebody at Duke did a type 1 error, and said, hey, look, we can predict it. Now, let's think about it. If you say somebody has cancer and they don't, I mean, their life's turned upside down. They could start chemo, which is very, very poisonous, very hard on the system because of type 1 error. There's an FBI fingerprint mismatch. When we do fingerprint analysis, we assume that any fingerprint that I get is not related to any other fingerprint. But sometimes it happens. Type 2 errors. Now, a type 2 error is basically when we have a false negative. We fail to reject the null hypotheses. And these are all, maybe I should pick something less bad, but basically Volkswagen emissions scandal. Regulators initially failed to reject the null hypotheses that Volkswagen cars were compliant with standards. So again, these are all things that are in business that can affect people, bottom line, money, everything else like that. So when you're doing a test or when you're doing research or when you're working on something, I want you to think about what is a type 1 error, what is a type 2 error. Now, when we look at levels of significance, or how do we know if something's special? How do we know if something's going to work? I mean, if we have 1 million fingerprints, what are the chances that one of them is unique compared to the other one? How do we know if we have something special? How do we know if our data, if we did an experiment and something happened, something worked? I mean, I look at all these P's and maybe one is smaller, but how do I know mathematically if that red P, not just based on color, how do I know if that red P is different than all the other P's? Well, you can't just look at it and say, I know it is because it's small. That doesn't always work. Again, the p-value statement, you can see I really want to drive this home. And I teach this in another class. So check this out. And this is why it's so hard to teach statistics, because I want you to understand really the fundamental ideas. Let's just say 90% of introductory to psychology textbooks that define or explain statistical significance do it incorrectly. So let's go back to the P here. So you go to college, you get a better education, and 90% of introductory psychology books explain if that is significant incorrectly. So that is why I'm less worried about the math and more worried about you understanding the concept of significance. So there's a t-test and a z-test. So the test statistic, let's just start with that. A test statistic is a standardized value that we calculate from a sample data that's compared to a distribution to determine the p-value. Ooh, that's horrible. There's a couple different types, like a chi-square, ANOVA, z-test, t-test. I'm going to go in a little bit more detail. Then, from your test statistic, we calculate a p-value. It's either 0.5 or 0.1. It can be slightly different. Most of the time, that's what it is. It's important to realize that when we calculate a p-value, we only do it per test. And I have another slide, and I know about that because I've seen that go sideways too. But it's a probability of obtaining the number we calculated, the test statistic, at least as extreme as the one observed, assuming the null hypothesis is true. Okay? So basically, if we have a small p-value, 0.01, 1%, 5%, it suggests that the evidence that we can reject the null hypotheses is correct. It's not always correct. 4% of the time will be incorrect, but it just suggests, or 5%, it just suggests that we're heading in the right direction. Okay. So we went over this already. So now, we talked about test statistics. So here's two types of test statistics. Or there's actually 4 or 5 on the screen, but let's just talk about z-test and t-test. Okay, I want you to comprehend, at least imagine in your mind, what these are. We can go over the math and all of these a little bit later, but so you have what they call student tests, a student t-test, independent test, independent t-test. About 10 different names for it, and they're all slightly different, but all basic idea, or z-test. And at the end of the day, those tests are basically for comparing two means. So if I want to take my student average, all your averages, we said, hey, at the end of the year, the average of my class is 92.3. Let's say I have 100 students, and we get my buddies Mike Lee, who taught this class once, like a couple years ago. We take Dr. Lee's score, and he had a 98, a 98.2, and he had 100 students also. Well, we can compare those means. T-test. So what is a t-test? A t-test is a simple way to compare an average or mean. A z-score is when you know standard deviation. T-test, not so much so. Now, hopefully this will help you remember it. I'm not a big drinker. I don't encourage drinking. It's hard on the body and the brain, but we're college students, so I'll make an exception. Does anybody know how t-test came to be, or student t-test came to be? I'll give you a hint. Guinness. So basically, let's see if I open the screen. Basically, a guy wanted to test beer who worked at Guinness, but he didn't want his boss to know, so he published it under the name Student. Let me get you some information on this. Desktop. Okay, there we go. Maybe this helps you remember it, because I want you to know what a t-test is. Again, what is a t-test? What are you comparing? You're comparing an average, you're comparing a mean. The student t-test, one of the most used statistical tests in medicine, was developed by a beer brewer around 1900 for the Guinness Brewing Company. One of the brewers was a mathematician and chemist. He developed a statistical method to deal with small survey samples. I guess you maybe couldn't drink a lot of beer and just couldn't test it. In the company t-test distribution table, Guinness enabled Guinness to make intelligent decisions about which ingredients to use, allowing them to produce high-quality beer that consistently tasted the same. He wanted to publish his findings, however, the beer said, nope, this would jeopardize their advantage over other breweries. So they came to a compromise. He was allowed to publish his findings under the pseudonym Student, hence student t-test. Yeah, that's how the t-test, you talk about business case, you talk about value, it's right here. So that's how you can remember t-test. It was used for testing beer. So chi-square test, what if we don't have two averages? What if we compare male versus female? Well, we can use a chi-square test for that. There's a bunch of different tests, but like I said, I wanted to get you a couple of the big ones. An ANOVA, and there's a ton of different types of ANOVAs. ANOVA is for, it's sometimes called like a three-way test or a multi, there's a ton of different names. But an ANOVA is for comparing means across multiple groups. So what if we took every class, or that's teaching IS 335? How do we compare that? Or what if we do some type of crossover study? I give you drug X for a month, and here's your mean reflex score, your mean running time. I take you off that drug, and test you again, and I compare it to other people and other groups and other universities. ANOVA. So, again, we cover this, but again, it's important that you know the z-test does what? Remember, the z-score is just kind of like a standardized, the standard deviation. It's just a standardized number. So it's used when the sample size is large and the population has a standard deviation that's known. The t-test, think in my mind, student t-test or beer test, is when the sample size is small or the standard deviation is not known, because I guess if you drink too much beer, you can't like do your statistics test. Chi-square test, when there's categorical variables. What's a categorical variable? Red, blue, green, male, female, tea or coffee, anything, first place, second place, third place. You're not actually comparing how much the difference between first place and second place is. You're just looking at big categorical variables. You're not looking at quantifiable numbers. You're looking at labels. ANOVA, for comparing means, so like a t-test, like a z-test, but across multiple groups. Now there is another thing we need to talk about, and it is the idea of tailed, or degrees of freedom, but we'll just keep it really simple and do a tail test. So one tail test or two tail tests. So a one tail test is a test in which something can only go one direction. A two tail test is it can go in either direction. Now, what do you mean? So if I am comparing my scores to Dr. Lee's scores, I know that his scores should be better or his scores should be worse. Two-tailed test. Now, if I want to compare my score to, like, it's hard to think of an example. If I gave you a drug and it only inhibited something and it could only have like maybe some type of negative impact, that might be a one-tailed test. Okay. If I have a car and I take a hose and make it smaller, the gas hose, the gas, I guess gas line, and cut it in half, I know that it can't go faster. So it just can't get enough fuel. It just physically can't go faster. So it's a one-tail test. Both horrible examples. If you guys want better examples, I can think of some for you. So now, let's talk about actually experimental terms, which should have been in the first part, but your book's kind of laid out like a crackhead. But a qualitative and a quantitative. A qualitative analysis is how many or how much or numbers. We employ statistical tools and mathematical models to analyze data. A qualitative analysis, a lot of times that could be text, it could be pictures, it could be Twitter, or is somebody happy? We attempt to understand why and how. So everything in Excel, pretty much what we've been doing is qualitative. A lot more of the world in the last 3 or 4 years is moving to qualitative. Did I get that backwards? Everything we're doing now is quantitative. Anything in Excel is quantitative. A lot of companies are moving to qualitative numbers. Still, I mean, a lot of the world runs on quantitative because it's what we have. But quantitative's slowly trying to move forward. It's just a lot more complex. So now remember, we have an independent and dependent variable. And it's okay if we get these mixed up. I did for a while. Let's uncluster them and let's figure them out. So what is an independent variable? It's a thing you change. An independent variable would be that gas hose. I have 3 cars. I change a gas hose for one of them. That's my independent variable. Now, what's the dependent variable? It's what I'm measuring. So maybe it's the fuel efficiency. Maybe it's the top speed. Maybe it's the acceleration of a car after I change the fuel line. If I give a bunch of students at UNLV vitamins, and I give a bunch of students at UNLV non-vitamins, placebo pills, the independent variable is the vitamins. The dependent variable is how tall they get, how well they do on school. Okay. Everything outside of your independent and dependent variables should be controlled, or you have confounding, or you have confounders. You have things that can affect this. And so when we talk about linear regression next week, we'll do something called R squared. And it's basically how well does one predict the other. And if you're at 80%, that means 20% is somehow uncontrolled. Maybe not the best analogy either. But. So independent variable is a one thing you change. The dependent variable is kind of what you measure. There's another graph I like. Cause, effect. Manipulated, measured. Like I said, you guys just really need to know this in and out, and You know, when you go out with your friends in 3 or 4 days, you know, hey, is this a better movie? And then is this not a better movie? Let me give you an example. It's a presidential election. I don't think I have this in this lecture. Okay, desktop was okay. So, um, back during the Obama campaign, they did an A/B test, and they found ways to get considerably more money from the same screen. I don't remember what one this one is or what one it is, but one of these things has pictures of the different A/B tests they ran. This is a great example. I just gotta click until I find something. Okay, right here. So they had some type of, you know, stock, hey, give me money, like this maybe. Or, you know, join us, learn more, sign up now. Okay. So sign up, sign up, sign up. So then they just changed, okay. So the independent variable, what was changed was maybe the flag versus the picture of Obama. So they changed that picture. What was the effect? What was measured? Donations. Simple change. There's Obama by, I don't know, like some ice mountains. There's a video of him. They changed it. That's an independent variable, is the picture. The dependent variable is dollars. $100 bills, yo. Well, it's money. Okay, so they measured the successful sign-up rate. So they're looking at conversion rates. The number of signups divided by the number of impressions. There were a total of 300,000 visitors to the page, below seen 13,000 people. The winning variation had a sign-up rate of 11% as compared to 8%. That's a 40% improvement. So just the difference in the picture, I guess, is a 40% improvement. It resulted in an additional 2.8 million email addresses on their list, which translated to $60 million in donations. So this is why it's important. And you would think that every presidential campaign, every business does all this stuff. They don't. They don't. If they do it wrong. But here's how we can just change one thing and somebody got $60 million more. And it's not hard to change. I mean, there's software, Google Analytics to do all this stuff. Easy to change, but 40% improvement, you had $60 million. That's in what, 1 year, 2 years? Yeah. I mean, it is crazy. You see the difference here. So that is why it's so important for us to understand. Let me get back over here. This concept, because businesses will want to change something, but then they don't know what they want to measure. So now, big data and hypotheses testing. So there's two things I kind of want to talk about this, and then I want to kind of cap it off here. But actually, I think I have a couple more slides. As we get more data, we can ensure accuracy more or less better. So if 10 people went to that Obama's page, it wouldn't be nearly as accurate as 300,000 people, which makes sense. Okay. However, the more people that go to it, the more costly it is, the more expensive it is. I mean, if he had that winning one up, the 40% increase one, the one that won, if he had that one up and he tested against a worse one, he would have lost $60 million. So that's why big data is important, but it's also kind of scary sometimes. Also with multiple tests, and I know I have another slide with that here. Yeah, we'll deal with this here real quick. When performing multiple hypothesis tests, the probability of incorrectly rejecting at least one true null hypothesis, type 1 error, increases. Without correction, this could lead to a false positive. Now, what do you mean? So if you perform 100 tests, okay, so I test 2 or 3 of the different Obama things. I perform 100 tests with a 0.05 p-value, significance level. You can just naturally expect that I will get 5 false positives by chance. So I'll have a type 1 error 5% of the time just naturally. Now there are ways to correct for this. Hopefully that's on my next slide. Yep, there is. So you can take the number of tests you do and divide it. There's a bunch of different ways. Bone for Only's correction is something I did a lot in genetics. But we adjust the significance level. At 0.05, we adjust that. Let's just say by dividing it by the number of tests. So 0.5, we do 2 tests. Maybe it goes to 0.25, we do 3 tests. Let's say 4 tests. Maybe it goes down to 0.12. This way, we reduce the chance of getting a type 1 error. But it's also harder to get to significance. In some of the health sciences, I think a more common one is a false discovery rate. Okay. So remember too, when you do multiple tests and you do things like bone for only, it's harder to get to significance. Type 2 error. So again, please just really spend time, try to get to know, try to really understand this concept. I'm going to include a couple of links of reading of optional and maybe a couple of videos. I know I got 1 or 2 up there now. I might include a couple more. Let's just go here. What's I can get out of this. You know, I don't normally review this type of stuff. Population is sample, you know that. A sample is what you kind of use to predict a population. Why do we do it? Because the census is $14 billion. It's a lot of money. A point estimate is just kind of the estimate that we use from the sample to predict the population. Okay. You have a confidence interval, or CI, and an interval estimate. This is how accurate we think our estimate is, or how accurate it should be, versus the range of our estimate. Okay. A null hypothesis is basically there's no effect, there is no difference. It's what we test. If there is a difference, we reject it and we accept the alternative hypotheses. It's important in science and business and everything else like that to state your null and alternative hypotheses. So let's just go with that Obama campaign. Hey, I changed the picture. There's going to be no difference between my sample level. There's going to be no difference between donations. I collected data, 300,000 people. I perform, if we're just looking at maybe a click-through rate or something like that, simple t-test. Decide whether or not to reject. I reject the null hypothesis. This black and white picture of Obama gets a 40% click-through rate compared to the other ones. I show Obama, dude, you got me $60 million more dollars. Do you want to be an ambassador? Do you want me to pay off your student debt? Whatever you want, you can have Richard. So, again, that's why we do the steps. We don't collect the data first, perform a test second, and decide, oh, you know what? Here's my hypothesis test. No. You have to basically state or write down, or at least, there's some sites you can register your hypotheses. Okay? Basically, you have to know kind of what you're getting into before you do anything. A test statistic is just, is it a t-test? Is it a ANOVA? How are we testing our data? Okay. Remember, a z-test and t-test are for comparing means. A chi-square is just for comparing categorical data. ANOVA is for comparing means between multiple groups. Independent and dependent variable. And I just thought about this. I do have, what is that guy's name? We'll leave you right here. Yes. So this guy was, I guess, a scientist. And he wanted to, and I've seen some of the videos like a long, long time ago on YouTube. Just do like the Randy challenge, or whatever, James Randall on YouTube. I'm not going to show you any of his stuff, but basically he would invite psychics up to kind of debunk them. He's like, hey, if you can show me, you can prove to me scientifically that you're a psychic or that you have extrasensory power, or you can basically reject the null hypotheses, I'll give you $1 million. Yeah, if you can reject his null hypothesis, he'll give you $1 million. Okay? Because so much of what we see on either TV or this, it's not controlled. So he developed the term blah, 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 blah. It's just because he had so many crazy people applying, okay? What else? Okay, so like here, like He tested 4 people for dowsing ability, which I think that using that stick. Yeah, the stick. The prize at the time was $10,000. So conditions were 10 by 10, 33 by 33 feet area, water supply and a reserve just outside the test area. So like for his examples, everyone's blinded. Yeah, okay. The rules had to be stipulated, and they must agree. So you have to set up your, null hypotheses before. The experimental conditions themselves do not negatively affect the claimant's ability to perform, or non-blinded preliminary controls are often performed. Okay. Claimants agreed to be readily observed prior to the test. Results are ambiguous or clearly indicated the criteria have not met. Remember, he has never had anybody win this. He stopped doing this, but he's had that famous psychic. I don't even know her name, but she was, Sylvia Brown was supposed to be on it, but she could never agree to the terms. Blah blah blah. So yeah, dowsing would place 10 100 pegs on the ground. Blah blah blah. So it's really interesting because, like I said, if you kind of set up your experiment correctly, it provides a lot more credence and a lot more validity to your results. So just keep that in mind. That's why this stuff's so hard, because everything that we read about in the media, news, and things like, oh, statistic this, it's just not accurate. So if you guys have questions, I'll be happy to share more links, more YouTube videos. There's a couple of things on Web Campus right now. You can go over your book. Your book covers pretty much the same thing. Have a great day.